Okay, so we talked about dot product and inner product. Now it's time to speak a little bit more about the geometry of three-dimensional space. So we want to talk about the geometry of three-dimensional space. We show this three-dimensional space with R3. So the most important objects in geometry probably are lines. Well, in geometry in plane, we have lines. A triangle is the result of having three lines which they are not parallel, right? In three-dimensional space, that's also the case. The lines are very important things in three-dimensional space. Now, on plane, lines are either parallel, like this, or they are not parallel. They have intersection, like this, right? In three-dimensional space, it's a little different. In three-dimensional space, two lines can be parallel. In three-dimensional space, they can intersect. But there is also another situation. Can you see that? Does anyone know what is this third situation? Is it possible for a line to be parallel, not parallel, but not having intersection too? Well, how are they going to look like? Okay, so I can try to draw it. It can be something like this. We can have a line here. Suppose below this line in another height, you have another line like this, right? They're not intersecting. One of them is above the other one, right? This one, say L1 and L2. We have two lines here. You can just try it with your fingers. One of your fingers is above the other finger. They're not parallel, but they do not intersect. And as the dimension goes higher, there are a lot of different situations we can have. This is usually, they're called skew lines. Parallel lines, sometimes they're parallel, sometimes they intersect, sometimes they don't intersect, but they're not parallel either. Okay, so we have more variety here in three-dimensional space, right? So in two-dimensional space, if you look at the coordinate system in two-dimensional space, we had X and we had Y, right? And any line can be described by using 2 points. If we have point P and another point Q, there exists exactly one line which passes through these 2 points, right? There's just one line which goes through these 2 points. And that's the important thing about Euclidean geometry. For any 2 points, there is exactly one line. There is a unique line which passes through those 2 points. And then this is the geometric side. But in the algebraic side, we can write down equations for these lines, right? So remember, algebra and geometry, there is a really correspondence between them. In geometry, we tend to see things intuitively. In algebra, we want to write things using equations. So if this point P here, if its coordinates are x1 and y1, and if this point Q here, if the coordinates are x2 and y2, we define M to be the slope of this line to be y2 minus y1, x2 minus x1. And with that definition, the equation of this line would be y is the variable, minus y1, the second coordinate of the point P, equals m times x minus x1, right? That would be equation of a line in plane. So for example, if they ask us write down the equation of a line which passes through 2 points, say P 1 and 2 and Q 3 and 4. If we want to do that, we should say, okay, if P is 1 and 2 and Q is 3 and 4, we should first compute this law, M. It's gonna be 4 minus 2 over 3 minus 1, which is 2 over 2, which is 1. So M is 1. The slope here is 1. And the equation would be y minus y1. Here it's 2 is equal to m, which is 1 times x minus x1, which is 1 here. It means y minus 2 is 1 times x minus 1, which is just x minus 1. If we add 2 to both sides of this equation, 1 minus 2 plus 2 is y, x minus 1 plus 2 is just x plus 1. That would be the equation of this line. Now, just like this, that we have equation for lines in plane, we can write down the equation of lines in 3-dimensional space. Okay, it's a slightly more complicated. There are different ways to do that. And it's a slightly more interesting. Well, 3-dimensional space is definitely more interesting than 2-dimensional space. Okay, so there are different ways to describe a line inside 3-dimensional space. The first way to do it is called a parametric equation or parametric way. So the first topic is parametric equations of a line in space, in 3D space. Okay, so look at 3-dimensional space. We have this coordinate system x, y, z. Okay, in order, if I want to give you a line, if I want to tell you about a line, there are 2 things I need to tell you. If I give you a point P, which the line passes through that point, and then if I give you a direction, say V, which that is the direction of the line, that uniquely would give you the line. I mean, there's just one line passing through P in direction of V, right? And that would be this line. So if one has a point P and a direction V, using these 2 things, you would get a unique line, right? Now, this P is a point in 3-dimensional space, and this V is a vector in 3-dimensional space. So P, its coordinates would be something like A, B, C. It's a point in 3-dimensional space. And this vector V is a vector in 3-dimensional space too. So its coordinates would be something like V1, V2, V3, right? Now I want to write down the line. I want to write down the equation, so-called parametric equation. Of a line, or of the line. There is a unique line which passes through P, the point P, and is in direction of V. What is that line? Okay. So the equation, there are three equations describing this line. So let's look at this line again another time. This is that line, the blue line, right? There are points on this line. Any line is union of infinitely many points. There are a lot of points on this line. So these points, they have coordinates like x, y, z. The coordinates of these points on this line, they satisfy three equations. So x, y, z. They're equal to, well, they're equal to a, b, and c. Remember, a, b, c are the coordinates of this point, plus, and now plus, well, here we are showing it with v1 times a parameter t. T is kind of, you can think about it as time variable. I know it might be a little confusing if you haven't seen this thing before. Just stay with me. We would understand it in a few minutes. Y would be b plus the second component of v, v2 times t. And z would be c plus the third component of v, which is v3 times t. This is called the parametric equation. Just for a second, just we can ignore what it really means. Let's just write down the equation. Let's just learn how to write down the equation. So for example, a question in the exam might be something like this. Write down the equation of the line which passes through the point P. This coordinates say 1, 2, 3, and is in the direction of a vector v with coordinates say minus, say 1, minus 1, minus 2. Okay, so we are in three-dimensional space. X, Y, Z. We have a point P. The coordinates are 1, 2, 3. So 1 in direction of X, 2 in direction of Y, and 3 in direction of Z. P is here. Okay, I can erase these things. I don't need them anymore. P is there. Now there's a vector V. I would draw that vector. I would start that vector at the point P. Okay. So I kind of, what is this vector? This is 1. So that in direction of X is 1. In direction of V, it's -1. So it would go to left -1. And in direction of Z, it's -2. So it would go down by 2. Now if I connect origin to that point, I would get the V. Right? This is the vector V. Now move that vector V such that the initial point of V would match P. So just move that vector V here. So I move the vector V such that the initial point of V is on P. Okay. Remember, we are allowed to move the vectors around. We can move the vectors around. So we will come here. It would be something like this. And then we want to look at the line which passes through P and it's in direction of V. This is going to be that line. Okay, now they ask us to write down the equation of this line. So this is the geometry part, to be able to draw the line and look at the line and see how does this line look like and things like that. In the algebra side, we should write down the equation. So x, what you should do is that you should say any point on this line, x, y, z, in some sense at time t, it's good for now to think about t as a parameter like time. As time t is at the point x, y, z. This point x, y, z is equal to, well, first we should write down the coordinates of p, 1, 2, 3, plus these numbers in v times t. So plus 1 times t, plus minus 1 times t, plus minus 2 times t. So that would be the equation, the parametric equation of this line. So for example, when t is 0, you can see where this point is. When t is 0, it means x is 1 plus 0 times 1, y is 2 plus 0 times minus 1, z is 3 plus 0 times minus 2. 1, 2, 3. So at the time 0, we are exactly at the point t, right? Where is this point at time t equals 1? Well, let t to be equal to 1. X would be 1 plus 1 times 1, it's 2. Y is 2 plus 1 times minus 1, it would be 1. And z would be 3 plus 1 times minus 2 would be 1. This new point, let's call this new point Q. This new point Q would be somewhere around here. If you set t to be equal to 2, you would find a point which is here. If you set t equals to 3, you would find a point here. If you set t equals to minus 1, at the time minus 1, you would find a point here. So in some sense, we are telling at each time t, where is something which is kind of walking on this line at different times t. That's what we mean by parametric equation, and that's how we should write it down. Okay, so yeah, is there any question about writing down this parametric equation?
I'm confused where the equation is.
Okay, let me write down the equation again. So we have a point P with coordinates A, B, C. And we have a vector V with coordinates V1, V2, V3. Okay? We want the line which is going to pass through P and it's in direction of V. We should move this vector V to P. So it would be like that. Just move this vector here. I want to find the equation of the line which passes through P and is in direction of V. It's something like this, right? I'm saying the points on this line, their coordinates are of the form x, y, z. X, y, and z, they are given by these equations. X, well, at the time 0, we are assuming we are at the point P. So x is equal to a, because the first component of P is a, plus v is the direction. You can think about v as the velocity. After t seconds, the point x, the number x would be equal to a plus t times v1. Y would be equal to b plus t times v2, and z would be equal to c plus t times v3. Now, if you, these are the equations. A, B, C are the components of the point. V1, V2, V3 are the components of the vector V. What does these, what do these equations mean? What do they mean? It means, well, if you set t equal to 0, it would tell you where you are at time equal to 0. You would be exactly at the point t. If you set t equal to 1, it would tell you where you after 1 second. If you start from p and if you walk in direction of v, you would be here after 1 second. If you let t to be -1 in these equations, if you substitute t by -1, it would tell you where you've been at t equals to -1. You would have been here.
So just to be clear, if t is at 0, then x, y, and z are equal to p, right?
Yeah, exactly. Because you are starting at p and you are going into the direction of v. So if you are starting at t at time t equals 0, you would be at p. But the point is that you want to know what is your position at each time t. Yeah, so the
then
thing
to answer the question that was asked, write down the equation of the line which passes through. So the question that was asked in the previous slide was write down the equation of the line which passes through p equals 1, 2, 3.
For some reason, I didn't hear you. Would you repeat?
Okay, so to answer the question that was in the last slide, what is is it one equation or is it x, y, and z?
Well, there are in some sense 3 equations.
Right, so it's the x, y, and that's the answer, the x, y, and z equations.
Yes,
okay.
Yeah, 3 of them together. So let's see. So as I mentioned, the thing we need to know, for example, for the exam or for the book, is to be able to just write down the equation. So let's do that. So you do this one. Write down the parametric equations of the line which passes through P, through the point P, and is in the direction of a vector V, and also tell me where, if we have something which kind of runs along this line, where it's going to be, if we think about V as the velocity, tell me where this particle, so if this is a line, if there is a particle, if it starts at P, where is this particle gonna be at the time t equals 3? Think about this for a few seconds. Try to write down the answer, and then I would explain again more carefully, and then I would write down the answer. Okay, let me write down the answer. I think all of you are right.
I have a question, sorry.
Yeah?
So this isn't what the answer, but will we have to do it, obviously, I think most of us did it algebraically, I would assume. Are we gonna have to do it geometrically, or is it just,
no,
we
it's
have to
more
do the graph stuff?
No, you don't have to, but well, while I'm teaching, I like to have, I want to see the graph, and I want to see what is the line we are describing.
So you want us to draw the graph?
Not in the exam. If I want,
okay,
I would say that explicitly, right?
Okay, got it.
So let's do it. So the point P is -1, 0, 4, and the vector V is 2, 1, and 3. Okay, so again, let me draw the graph to see which line we are thinking about. So the point P goes into direction, in X direction, it goes back by 1. It wouldn't move in Y direction, it would go up by 4. So this is where P is. This is P. Let's look at the vector V. In direction of X, it would go forward by 2. In direction of Y, it would go right by 2. In direction of Y, it would go up by 2. Okay, it's a little hard to see now. Maybe I should have moved in direction of Y a little more. Say this is 1, 1, 2, 3. Say this is the terminal point of V. And then I should connect the origin to that point. I would get the vector. Now we should move this vector to P. We should move this vector exactly, just move this vector to P. And then there's a line which passes through the point P and its direction of V. Okay. And we want to write down the equation of this line. X, Y, and Z, by definition, are equal to, well, X is equal to first coordinate of P, which is -1, plus the first coordinate of V, which is 2 times T. The second coordinate Y is equal to first coordinate of P, which is 0, plus second coordinate of V, which is 1 times T. 1 times T is just T. Z, the last one, is equal to the third coordinate of P, which is 4, plus the third coordinate of V times T, which is 3 times T. So these are the parametric equations. Now, if we have a line, I would write again here. This is P, this is V. A particle starts here at time t equals 0, and it walks in direction of V. We want to see where it is at t equals to 5. We should just plug in into our equations t equals 5. Or for any other time. I think I ask for t equals 3 actually. So, well, X would be -1 plus 2 times 3, which is 6 minus 1 is 5. Y would be equal to 0 plus 3, which is 3. And Z is equal to 4 plus 3 times 3. It's going to be 9 plus 4, it's 13. So it would be at the point 5, 3, 13. That would be the coordinates of this point after 5 seconds. So starting from P, going in direction of V with the velocity given by V. Okay, so that's how the parametric equations help us to understand the lines and to describe particle kind of walking along, moving along that line. There is another way. There's a second way of describing the lines. There is a different way of doing that. And well, some people prefer this second way I'm going to mention now. It's called the symmetric equations of a line. Symmetric equations of a line. Is there any question about how to write down the parametric equation of a line? I know it might be slightly confusing. What I want you to know now is just to be able to write down the equations. If I give you a point P and if I give you a vector V, I want you to be able to write down the equations. Okay, so if in three-dimensional space, if we have a point P here, and if we have a vector V here, it would give us a line passes through P in direction of P. So if P, the point P is, Well, I would use a slightly different letters. Say P is given by x1, y1, and z1. And the vector V is given by, say, ABC. Okay. I just constantly change notation, so you wouldn't really get used to a fixed notation. The notations do not matter. So the equation of a line would be x, y, z equal to, well, x would be equal to P. What is P? It's x1 plus T times the first variable of V, which is A. It would be AT. Y would be equal to the second component of P, which is Y1, plus the second component of V times T, which is BT. And finally, Z would be the third component of P, which is Z1, plus third component of V, which is C times T. Now, for a second, for simplicity at this moment, suppose A, B, and C, all of these numbers are non-zero. Okay? Suppose they are not zero. Suppose V is something like 1, 2, 3. Suppose they are not zero, right? Look at the first equation here. I can subtract x1 from both sides. On the left side, I would get x minus x1. On the right side, x1 would cancel with minus x1. So x minus x1 is equal to AT. Now look at the second equation. Do the same thing with y1. So y minus y1 would be equal to BT. And do the same thing with the third equation. Subtract z1 from both sides. Z minus z1 would be equal to CT. Okay? Now, again, look at the first equation. I can divide both sides by A. X minus x1 divide by A. On the right side, AT over A. AT over A. Well, A and A, they cancel each other. So we would end up with just T. So I would write down just T. If we divide both sides by A, we would get x minus x1 over A equals T. If we divide the second equation, both sides of the second equation, by B, I would get y minus y1 over B equals BT over B, but B and B would cancel. They would cancel each other. It would be equal to T. The third equation would give me Z minus Z1 over C equals T. I'll write down these in the next page. So x minus x1 over A equals T. Y minus y1 over B equals T. Z minus Z1 over C equals T. Can anyone tell me why did I assume A, B, and C are non-zero? What would happen if A or B or C, if one of them is zero? Yeah, so if I understand what you mean correctly, if one of them is zero, then we are dividing by zero. We can't divide by zero. Since we can't divide by zero, we should assume A and B and C are non-zero. But now look at here. T is equal to T. So if x minus x1 over A is equal to T, and T itself is equal to y minus y1 over B, these two things have to be equal, right? On the other hand, y minus y1 over B is equal to T, but T itself is equal to Z minus Z1 over C. So these things, they have to be equal. So x minus x1 over A is equal to y minus y1 over B is equal to Z minus Z1 over C. The equation we have here is called the symmetric equation of a line. So if I want to summarize. Symmetric equation of a line which passes through a point P with coordinates x1, y1, and z1, and is in direction of a vector v with coordinates a, b, c. The equation of this line is x, y, and z such that x minus x1 over a is equal to y minus y1 over b is equal to z minus z1 over c. This is the symmetric equation of a line. So for example, the question can be write down the symmetric equation of a line which passes through a point P with coordinates 1, 2, 3, and is in direction of a vector V with components -1, 2, and 3. Well, it would be x minus the first coordinate of P, which is 1, over the first coordinate of V, which is -1, equal to y minus the second component of P, which is it would be -2, divided by the second component of V, which is 2. It is equal to z minus third component of P, which is 3, divided by third component of V, which is 3. This is the symmetric equation of a line. Okay, so we have two types of equations for a line. One is parametric equation, the one with the time variable, the parameter t, and the other one is this equation, where there is no time parameter. There's no t here. No t. Well, in some sense, you can allow all of these things to be equal to t, and you would get back what you had. But in the equation we have here, we don't see any t. Okay.
So just to clarify, for parametric equation, it's 3 equations, whereas for symmetric, it's those 3 equations put into one equation.
Yeah, exactly. So here, well, here it says this is equal to this, that this is equal to this. So in some sense, there are 2 equations here. Well, you can also say, because the first one equal to second one, the second one equals to the third one, the first one is also equal to the third one. But anyway, we kind of summarize all of them in one line in symmetric equation. Whereas in parametric equation, we had 3 different equations. Yeah, it's the transitive property of equality. Okay, so that's how we write down the equations of a line in 3-dimensional space. But what if the vector v, what if they tell us, write down the symmetric equation of a line which passes through a point P with coordinates 1, 2, 3, and is in direction of V equal to, say, 1, 0, 2. What can we do then? I mean, if we want to do exactly what we did here, we should say x minus the first component of P, which is 1. We should divide it by first component of V, which is 1. We should say this is equal to y minus the second component of P, which is 2, divided by second component of V, which is 0. It's equal to, should say, z minus the third component of P, which is 3, divided by third component of V, which is 2. But it doesn't make sense, because here we have y minus 2 equals 0. This does not make sense. What can we do about it? The answer is simple. Just get rid of that, forget about y minus 2 part, you would get x minus 1 over 1 equals to, well, this one makes sense. This is equal to z minus 3 over 2. Yeah, you're right. One comment, I got one comment, and that's correct. We have this thing. Look at here, when this component is 0, y always would be equal to this component, the second component of p. What does it mean? We should say x minus 1 over 1 is equal to z minus 3 over 2, and y is always equal to 2. Y would be always equal to this second component. That would be the equation. Let me write down one more example. So if we want to write down the symmetric equation of a line which passes through the point 1, 2, 3, and is in direction of the vector v 0, 2, 3, if we write down the equation, it would be x minus 1 over 0 is equal to y minus 2 over 2 equal to z minus 3 over 3. But x minus 1 over 0 does not make sense. It's not defined. So we get rid of that. We say y minus 2 over 2 is equal to z minus 3 over 3. And x would always be equal to the corresponding component of p. Here is 1. It would be always 1. And so this is going to be the symmetric equation of this line. What if there are two variables which are always constant? What would be the equation of a line p? Of a line which passes through the point p 1, 2, 3 and is in direction of vector v, which is 0, 0, 1. How can I write the equation of that line? Think about that for a few minutes. What would be the equation of a line which passes through p and is in direction of v? So this idea doesn't work anymore, apparently, and that's correct. Because if we try to do that, we should write x minus 1 over 0 is equal to 1 minus 2 over 0, which is equal to z minus 1 over 3. Well, this would imply x is equal to 1, and it would imply y is equal to 2. But what about the last one? Z minus 1 over 3 equals what? I mean, equation should have two sides. Something should be something, it should be equal to something else. But z minus 3 over 1 is, there's nothing for this thing to be equal to. Yeah, in some sense. Basically, the equation is pointless. You can't say it's equal to 3 because all of these things were equal to 3. But what I want to say is that the equation would be pointless because it basically means z can be 3 times t plus 1, but this is, well, it makes sense if there's something to say about x and y too. The correct way to write this thing, so let me go to the next page to explain it more carefully. So the correct way, when we have a vector v 0, 0, and 1, and the point p equals to say 1, 2, and 3, the correct thing is that you are right, it implies x can be equal to 1, y can be equal to 2. There is no third equation because z minus 3 over 1, there is nothing for that to be equal to. So there is no equation for z. There is no equation for z. When there is no equation for z, it means z can be anything. There is nothing we can say about z. Z can be anything. So we don't say anything about z. The only things we say is that x is equal to 1 and y is equal to 2. Okay. So in some sense, there's no parametric equation left anymore if 2 of these are 0. And if all 3 are 0, it doesn't make sense anymore because, well, what is a line which passes through P and is in direction of V? If the direction of V is 0 direction, there's no direction and there's no line. So we wouldn't get any line if all of the components are 0. Okay, so that would be our definition of lines. We have 2 types, therefore remember there's parametric equation, and then there is this symmetric equation. Okay, any question about lines and their equations? Okay, so we should continue. Well, we got to planes. I prefer not to start planes directly now. Let's see. So before going to the next topic, I want to have a little, well, I don't want to be very fast, to be honest. So let's talk about the little random things. Yeah, I would prefer to spend a little time to kind of learn. We should learn how to solve problems, problem solving techniques. So problem solving techniques. Suppose we have a room with a lot of, say, students there. We have so many students there, a lot of them. And they have hats, and the hats are in 2 different colors. Let's say half of them have hats which are green, not necessarily Stony Brook hats. And some of them have hats, not half, just some of them have red hats. Let's draw a few more. Suppose there are many of them actually, okay? And what I want to do is that I want to ask them to stand in a line. I want to ask them to stand in a line such that the guys with the red hat are next to each other. So something like this. Such that the guys in red hat are next to each other. And the guys with the green hat, people who have green hat, the students with green hat are next to each other, right? But the problem is that there are 2 rules. One, they can't see the color of their own hats. They can't see the color of their own hats. 2, they can't speak to each other. So they can ask someone else, what is the color of my hats? How can they stand in a line in such a way that the students with red hat are next to each other, the students with green hat are next to each other, while they don't know the color? There's no mirror. So let's solve it without like mirror and like taking a photograph or anything like that. So we want an honest mathematical way of, not mathematical, actually there's nothing mathematical about it, an honest way of solving this problem. How they can stand, so there's no mirror. So really suppose you are in a room with some other students. Suppose you are one of them. And suppose you have a hat and you have no idea if your hat is green or if your hat is red. And you all want to stand in a line and you're not supposed to talk to each other. How can you do that? What do you mean you would see your own hat? One of the things, one of the rules is that you cannot see your own hat. You don't see your own hat. So you have no idea what is the color of your hat. Yeah, you can't see that in the mirror. Yeah, you're not supposed to stand in front of the mirror. You're not supposed to know what is the color of your hat. And the other people are not supposed to tell you either. Any idea? Actually, it's not hard. It's not very hard, but it's very interesting. Is the question clear? Do you all get the question? Yeah, okay. Yeah, good. And it is, in fact, it is an important question, although here it looks like a very interesting puzzle. It is a deep question. And it has a lot of applications, but well, what do you mean by the color doesn't matter? I mean, at the end, we want them to kind of, we want to separate them. We want to separate the people with the students with green hats. We want to separate them from the students with red hats, right? No, they cannot use hand signals. They are not supposed to speak each other. They're not supposed to show hand signals. They're not supposed to do those things. They can, well, no, they are not allowed, they are not allowed to exchange hats either. They have their own hats. They're not allowed to exchange hats either. They have their own hats and they should. Yeah, suppose they also know, yeah, suppose you are one of those students yourself. You know there are two colors, you know how many students are in the room, and you just want to stand where you should stand, you know. Okay, Christopher, you kind of have a point, but can you explain more carefully? Can you elaborate on that?
So if you have, if you see only a green hat in the line, if it's, let's say it's the first person is a green hat, you can go behind them, and it doesn't matter if you're green or red. And then if you see, then it'll be, if it's two greens, then you still go behind them. But if it's a green and a red, no matter what you'll be.
That is correct.
Yeah, if you, it's kind of hard to explain.
No, I got it. You understand. So the answer, yeah, that is correct, and it's okay. It works. Let me explain. So, suppose you don't know what's the color of your hat, right? You have no idea, right? But just stand somewhere, right? The first person can stand anywhere. Just stand somewhere in the line. Okay, you're the first person. The second person, again, the second person can stand anywhere. It really doesn't matter. Either the hats are the same color or they are different colors. Say they're the same color, right? Now the third person comes. So the third person, look, well, if you have the same color, well, if these two people have the same color, you don't see the color of your own hat, but this person, suppose, see there are two people with green hat. Suppose this new guy has red hat. He doesn't know the color of his own hat, but he only sees there are two green people. He can just go, this new student can just go and stand next to them. Doesn't see the color of his own hat, but he just goes and stand there, okay? A new student comes. She has a green hat, okay? She can see these guys, right? She can see two of them have green hats, one of them has red hats. She should always go and stand between them. So she should go there. She should be here. Then it would be like this. Then a new person comes. So suppose she has a red hat. She doesn't know the color of her own hat, but it doesn't matter. She should just go and stand between them. So she should come here. Now suppose a new person comes. He has green hats. It doesn't matter. He should just go there and stand between them. And as long as these, so I would just show the hats. So for example, you have a line of hats like this. When a new person comes who doesn't know if his hat is green or red, he can see the hats of the other people. He just should go and stand between the red and green guys. And the next person comes, her hat is green. She doesn't see the color. She can't see the color of other hats of other people. She should just stand between them. And in that way, the red hats and green hats are always separated. Although you don't know the color of your own hat, but as long as you go and stand between them, you are on the correct spot. And the next person should do the same thing. Does it make sense? If it's confusing to you, raise your hand. I would explain again. Not confusing for anyone? If it's not confusing for you, raise your hand. If you understand the solution. Okay, so if it makes sense, we can continue. If you are still confused with this idea, I can explain further. So that's a way to sort things while like each person doesn't know if, well, in this case, doesn't know the color of his or her own hat. Well, and it's a serious question actually, but we just considered it in a kind of interest in this interesting puzzle. Okay, we can have a short break. Let's continue with one more interesting concept, and then after that we would continue with planes. Okay. Before that, I want just to introduce one interesting concept. So let's go back. Okay. I want to tell you something about what is known as chaos theory, which is related to, in some sense, is related to the simulations we had earlier. You know, in math and in nature, if say there's an object here, and it's three-dimensional space, and you have an object here, and it goes in some direction, V. And there is and there are some forces, and there are some, I don't know, suppose it's a planet, it's Earth, for example, and it's sun here, and Earth goes around the sun, something like that. If we move Earth to another point, which is close to P, say Q, and move it in direction which is close to the direction of V, say U. If we just move, these are called the initial conditions. The first, the position the planet starts to orbit and the direction of the orbit. If we change them slightly, not very much, So if we just change them a little bit, well, the final result wouldn't change a lot. So for example, if we move Earth a little and move the direction of the speed of Earth a little, for example, after a few days, rather than Earth being here, Earth would be in another close point. So say P prime, Q prime. It's not, well, if we change the initial condition slightly, this is called initial condition, where it starts and the direction of speed. The final situation would they also would be close to each other. However, that's not always the case. Sometimes if we change initial condition a little bit, it changes the result a lot, right? For example, well, in some cases it's true, in some cases it's not true. For example, if you exercise every day for 1 hour, you would get some result after a month. Now, if you exercise every day for 1 hour and 1 minute, the result you would get after a month is not going to be very different. 1 minute more exercise or less exercise probably is not going to affect the final results much, right? But that's not always the case. Sometimes changing the situation a little would cause in a huge amount of change in the final result. Let's see an example of that. Okay, I would share my screen. Do you see my screen? Look at these two trajectories. Okay, maybe I should go back. Look at these 2 points, okay? First of all, can you guess these 2 objects? What are these 2 objects? Are these planets or what? These are trajectories of something, but trajectory of what? Is there any guess? Let me read your messages. Sorry, I couldn't see them. Yeah, that is correct. You see, the brown object has a chaotic behavior. It's a double pendulum. It has chaotic behavior. And it's almost impossible to predict how it's going to, its exact trajectory actually. So look at these objects. They're all close to each other, right? So the starting position of all of them are close to each other. But as you would see, although they are close to each other, initially they are close to each other, very soon they would have very, very, very different trajectories. Okay, so this is called a chaotic system. I didn't read the title actually. What was the title? The title was the, okay. Okay, so this was an example of a chaotic system, and it's interesting to look for them in nature. This was another example. You can construct a double pendulum even at your home. It's pretty simple. There are other examples in the nature too, and it's pretty interesting. Okay, let's continue. Let's continue with the final topic we are going to talk about today, and that's about planes in space. We talked about lines, right? We had lines, these kind of lines. Now we can talk about planes. Planes are like this, like a piece of paper. They go to infinity in all directions, just like a line. You have a line L, you have a plane P. Okay, so in order to, if I want to find the specific line, there are two ways to do that. Either I can choose 2 points, P1 and P2, and then I can say the line which passes through these 2 points, and there would be one line, one unique line which passes through these 2 points. That's one way. The other way is to give 1 point and 1 direction, and I can say look at the line which passes through that point in direction of V. That would be that. So there are 2 ways to fix a line. What about a plane? What are the information I need to specify a plane in the space, like planes like these? What kind of equation they need? Before that, let's see what different situations 2 planes can have with respect to each other. 2 planes, just like lines, which they could be parallel in 3-dimensional space, they could be parallel, they could be so-called transversal, they can have intersection, or they can be skew. One of them can be above the other one. They're not parallel, but they don't have any intersection. There are 3 cases for lines. There are different cases for planes too. Well, 2 planes, they can be parallel. This is one plane. This is another plane. They are parallel. They don't have any intersection. The other case is when they have intersection. So this is one plane. This is another plane. And they cut each other. They have intersection. Just like you can see that with just like a book. If you open a book, if you have a book, if you just open the book, it would look like this, right? It's like this is like one plane, this is like the other plane. They intersect along a line. So 2 lines intersect along a point. But 2 planes intersect along a line. The intersection of 2 planes is a line. Is there a third case? So this is first, this is second. Is there a third case or not? Is it possible for planes to not have intersection along the line and not be parallel? Is there any other case which I've missed here? No, in 3-dimensional space. Yeah, you're definitely right. In higher dimensions, there are more strange things, but in 3-dimension, both of you are correct. In 3-dimension, there is no other case. They're either parallel or they intersect along a line. Okay, so now we want to specify a plane. Any plane actually can be described by first a point on the plane, say a point P. This is 3-dimensional space, X, Y, Z. A point on the plane P with coordinates, say X1, y1 and z1, and a vector. Which vector? The normal vector. We showed with n. So any plane, if you just look at a plane, you can fix a normal vector. So at each point, there are two directions which are orthogonal to the vector. One is this direction, which is orthogonal to the vector. One is the other direction, right? There are two directions. If we choose one orthogonal vector to a plane, for example, this one, I would choose this one, and one point, say P, using these two pieces of information, we can completely describe the plane. So let's see. Let's first geometrically look at that. If I tell you P is a plane, so let's say we have a plane, which this plane contains P, and this is the point P. And this vector n is normal vector. N is normal vector. It means it's normal, or well, we call it normal vector. It means it's orthogonal to all vectors in the plane. If I ask you what is that plane P, it's not hard to see that. It's supposed to be a plane which has this point P, and it's supposed to be normal to this vector. That uniquely gives this plane. I mean, maybe my drawing is not very clear, but there is just one plane which has this point and is normal to a given vector. Right? You can see that. You can look at your pen. You can think about it as a vector, right? And you can think about the tip of, like the tail of your pen, for example, as the point P. Okay. You want to have a plane which has this point P and is orthogonal to this vector, which is your pen. So suppose your hand is your plane. It's supposed to be normal to your pen. There's just one way to do it. Maybe it's better if I show it to you. Okay, suppose this is the vector. This is the normal vector, right? And this is the point P. I want a plane which passes through this point and is orthogonal to this vector. Well, this is just, there's just one, this one. If I fix this one, there would be just one plane. So that's how we kind of explicitly describe planes with a point P and the normal direction n. And that would give us a plane which contains this point P and has the normal direction. So if the point P has coordinates x1, y1, and z1, and the vector n, the normal vector, n has the coordinates a, b, c, the equation, well, this is the geometric way to see it. This is geometry, drawing the graph. The algebra is writing down the equation, the algebraic equation, which is called the standard equation, actually, the standard equation of a plane in space, in 3D space, is the following. So it's supposed to contain P, and it's supposed to have n as the normal vector. The equation would be A times x minus x1 plus B times y minus y1 plus C times z minus z1 equals 0. That would be the standard equation of a plane. A times x minus x1 plus B times y minus y1 plus C times z minus z1 should be 0. So for example, a question in the exam can be something like this. Write down the equation of the plane of the plane in three-dimensional space, which contains a point P with coordinates 2, 5, -1, and has n equal to, say, 1, 2, and 4 as the normal vector. Well, the equation would be A, which A here is this number, times x minus x1. x1 is this number, plus b, b is this number, times x minus y1, which is 5 here, plus c, which is this number, plus c, which is -1 times z minus z1, which is -1. -1 would be +1, equals 0. This would be equation of this plane. If you want to draw the equation and see where it is, we can also do that. The point P is 2, 5, -1. So we should go in direction of x by 2. 5, we should go in direction of y by 5. And -1, we should go down by 1. This is P. Oh, the last coordinate is 4. I made a typo here. Thank you. C is 4. Thank you. So this is P. And what is the normal vector? N. So the vector N is 1, 2, 4. If we connect the origin to that point, we get the vector n. Now we should move this vector to P. We should just move this vector and bring it here. Okay. What is the plane which contains P and is normal to n? It should look like something like this. The plane would look like something like this. And what we have here is the equation of the plane. Okay. Now we can continue this. So we have I would explain the logic behind this too. Yeah. So we have x minus 2, what is the equation? Plus 2 times y minus 5. No, I didn't. Plus 4 times z plus 1 equals 0. Okay, that's the equation. This is called the standard form. We can simplify it. Well, x minus 2 plus 2y minus 2 times 5 is minus 10, plus 4 times z plus 4 equals 0. Well, it means x plus 2y plus 4z plus, what is the rest? We have minus 2, we have minus 10 would be minus 12, plus 4, it would be minus 8. Equals 0. This is called the simplified equation, which is basically just the standard equation, but we multiply these numbers and simplify it a little bit. So this is called the simplified equation of a plane in three-dimensional space. Okay, the reason why this is true, so I wouldn't test you on this in the exam, but why is that true? So it's the proof. I wouldn't ask you for the proof in the exam or something like that. So if it's confusing for you, you can ignore that. But why that's the equation? So we have a point P with coordinates x1, y1, z1. And we have a normal vector n, a, b, c. And then there would be a plane which is normal, which is orthogonal to this normal vector and contains p. Any random point you choose on this plane has x, y, z, coordinate x, y, z. I want to find out what is the equation which describes any point on this plane. So I choose a random point, a general point x, y, z on this plane. And look, I would look at the vector which connects p to this new vector, new point. Look at this green vector. Connects p to this new point x, y, z. I would show this vector with v. What are the coordinates of v? Well, if you remember, coordinates of vector would be the terminal point minus the initial point, which is x minus x1, y minus y1, z minus z1, right? On the other hand, n is the normal vector, so n is orthogonal to every vector in this plane because it's orthogonal to the plane. So n is orthogonal to the vector v because vector v is a vector in this plane. It connects 2 points in this plane, so it is in this plane. What do we know about the dot product of two vectors which are orthogonal? Does anyone remember? It's 0, yeah. So the inner product should be 0. But what is inner product? Well, inner product is multiplication of first coordinates, first coordinate of a, the multiplication of coordinates and then adding them. The first coordinate of n is a, the first coordinate of v is x minus x1. The first coordinate of n, the second coordinate of n is b, the second coordinate of v is y minus y1, and also the same goes for the third one. This is their inner product, and it should be 0. And that's the proof. Okay, is there any question about the proof? So if you want to understand the proof and if it's confusing to you, ask me now. Okay, so that's the proof of the equation. Do we need to know how to find equation given 2 lines or 3 points? Probably, but whatever you can be sure that I wouldn't test you on something in the exam, which I have not told you that. So it depends on how much time we are going to have, because we don't have much time this semester. Well, the question you are referring, it's definitely in the book and you can read that. I might also talk about that, but if I don't talk about that, it wouldn't be in the exam. Okay. So I would test you only on things that I'm teaching here. Okay, so that's how to write down the equation of 2 planes. Now, if 2 planes are given, we want to see if what is the kind of situation 2 planes have with respect to each other. Let's go back to 2-dimensional case first. Look at the lines. Sometimes lines can be transversal. Sometimes lines are parallel. How can we understand that by just looking at the equations of these lines? So for example, let's say equation of one of the lines is y minus y1 equals m1 times x minus x1. That's the equation of one of the lines, say L1. And then I have another line. Equation of the other line is, say, something else. Y minus y2 equals m2 times x minus x2. Do you know when these 2 lines are parallel? Just by looking at the equations. Yes, exactly. If their slopes are equal, they are parallel. If M1 is equal to M2, they are parallel. If M1 is not equal to M2, they are not parallel. So for example, if I have a line y equals 2x plus 3, I have another line equals 2x minus 5, here I have 2, here I have 2, they are parallel.
What if the slopes are absolute values of each other? So what if one slope is 2 and the other one is -2?
Well, they are parallel, but they are in some sense, if we think about them as vectors, and they're in different directions. So you're right. I should, thank you for telling me. So actually, it's good to think about them as their absolute value. We don't care about sign. You're perfectly right. So for example, if even I have 3x minus 6 and I have minus, oh no, sorry. No, they should be equal. I confused something with something else. They have to be equal. So the point is that, well, I mean, that's a silly mistake. So for example, if a line is y equals to x, it's like this. If a line y is equals to minus x, so rather than 1, it has minus 1, the line would be like that. Well, these two lines are not parallel, right? The slope of one of them is 1, the slope of the other one is minus 1. So they have to be equal. If they are not equal, they're not parallel. Now, let's go to 3-dimensional space. We can have lines in 3-dimensional space. Well, as I said, the lines might be like this, they might be like this, and they might be like this. I want to just now mention one case, the case where they are parallel. So equation of, well, let's write down the symmetric equation. So symmetric equation was x minus x1 over y1, say, equals y minus y2 over b1, y1 over b1 equals z minus z1 over c1. Say this is the equation of a line L1. This is the parametric equation I just defined. Let's say I have another line, which its equation is something else. The parametric equation of a line would be something like this. Now the question is that how can I understand if they're parallel or not? When these two lines are parallel, how can I decide if these two things are parallel or not? No, not exactly. They shouldn't be, you're pretty close, but not exactly the same. That's the interesting thing. Now, if these, yeah, that is true. So if you look at one of these, if I look at this A1, B1, C1, and the other one A2, B2, C2, if one of them is a multiple of the other one, they are parallel. So if one of them is equal, the other one times a number, say, is equal to, I would show it with some number R, then they are parallel. So for example, if I have a line like this, x minus x1 over 2 equal to 1 minus 3 over 4 equals to z minus 7 over minus 3, and I have another line. And I want to see if they're parallel or not. I should look at the denominators here. The denominators here are 2, 4, minus 3. The denominators here are 4, 8, and minus 6. Are they multiple of each other? Can I get to one by multiplying the other one by a number? Yes. So 4, 8 minus 6 is equal to 2 times the other vector. If I multiply 2 by the other vector, 2 times 2 is 4, 2 times 4 is 8, 2 times minus 3 is minus 6. In that case, they are parallel. But if rather than minus 3, I had minus 4, then that wouldn't be true anymore, and they wouldn't be parallel. So that's the way to understand when two vectors are parallel inside three-dimensional space. Now we can ask the same thing for planes. If I have two planes, I want to see when these two planes are parallel. Remember, so if this plane, this is plane number 1, let's show it with A1, and plane number 2, let's show it with A2. Let's say the equation of A1 is something of this form. A1 x minus x1 plus B1 y minus y1 plus C1 z minus z1 equals 0. Let's say I have another plane, A2, which its equation is A2 x minus x2 plus B2y minus y2 plus C2z minus z2 equals 0. So remember, x1, y1, z1 is a point P1 inside this plane. And x2, y2, P2 is a point in the other plane. What is A1, B1, C1 is a normal vector. What is A2, B2, C2? It's a normal vector. Yep, that's correct. These two planes are parallel if I look at these two vectors n1 and n2, which is A1, B1, C1, and n2, A2, B2, C2, if one of these is a multiple of the other one. So for example, if I have a plane 2x plus 3 times 1 y minus 3 plus 4 times z plus 1 equals 0, and I have another plane, which is minus 4x minus 6y minus 3 minus 8z plus 1, yeah, I would go back. If I have a plane like that, these two planes are parallel because if I multiply 2 by minus 2, I would get the other one. So you see, all of these numbers are multiplied by minus 2. So they are parallel. Is there any question on this slide? Okay. So, and the reason is simple, because if I have two planes, if these two planes are parallel, their normal vectors are also parallel, right? If two planes are parallel to each other, the normal vectors they must also be parallel. And two vectors are parallel if and only if one of them is a multiple of the other one. So if two planes A1 and A2 are parallel here, N1 and N2 should be parallel, the normal vectors. And it means one of these vectors should be a multiple of the other one, which is the case here. The normal vector for the first one here is 2, 3, 4. The normal vector for the second one here is minus 4, minus 6, minus 8. If I multiply one of them by minus 2, by negative 2, I would get the other one. That means the normal vectors are parallel, which means these two vectors are parallel. But we can even go one step further. We can consider a slightly more general case. Is there any question here? Okay, maybe it's good time for me to write down a question. Are these two planes parallel? Well, I don't write them in the standard form now. I would write them like this. I would write them in the, well, maybe it's even better to put them on one side. I would write them in the simplified form rather than standard form. And now I'm asking, are these two vectors parallel or not? Well, what do you mean? We have equations. Well, we have equations of two planes. So we have those two planes. We can draw them and look if they're parallel or not. So there is enough, well, we have enough information. But the question is that how can we look at the algebraic equations and decide if these two planes are parallel or not? Okay, so it seems you're mostly towards the negative answer. You think they're not parallel. Okay, let me tell you that. It doesn't matter how I wrote down these equations. See, look at this equation here. 2, 3, and 4, they form the normal vector, right? If I multiply these numbers, what do I get? 2x plus 3y minus 9 plus 4z. So minus 9 plus 4 equals 0. Well, minus 9 plus 4 is minus 5. 2, 3, and 4 are still the coefficients of x, y, z. It doesn't matter if I write the equation in the standard form or if I write it in the simplified form. These numbers here still, they are presenting the normal vector. So it doesn't matter how I write down the equation. The normal vector for the first equation still is 2 minus 3 and 4. The normal vector for the second equation is, there's still the coefficients of x, y, z, 2, 3, minus 2. Is one of them a multiple by the other one? No, because, well, if it was 2 goes to 2, it seems it should be multiplied by 1, but then 3 goes to minus 3 and 4 goes to 2. So it's not like one of them is multiplication of the other one. That's not the case. Therefore, they are not parallel. Simply because one of these vectors is not a multiple of the other vector. Okay? Any question here? Okay, let's continue. So we can understand this thing even slightly better. If we have two vectors, if we have two planes in general, well, either they're parallel or they would intersect. See, for example, here I have two planes, they intersect. Okay, and they would have an angle between them, theta. I want to find this angle theta between them. So for example, here theta looks to be something like around 90 degrees. Here I can draw another case. Here theta seems to be, well, maybe I should exaggerate a little bit more. Here it seems we have a wider angle, right? Here.
I have a question super quickly about the finding parallels, finding if the vector is parallel. So yeah, for the example that you had before, you had let's say you had do x, y, and z all have to be the same multiple?
Yes, that's the point. So okay. For example, 2, 3, and 4.
It would have to be 4, 6, and 8.
They are a multiple of each other because if I multiply first one by 2, I would get the second one, right? But here I had 2, minus 3, and 4, and I had 2, 3, and minus 2. There is nothing which I can multiply by one of them to get the other one, right? Because if I look at the first one, it looks the number I should multiply with should be 1. But if I look at the second one says, no, it's minus 1. And if I look at the third one says, no, it's minus 2. So there isn't anything like that, right? Yeah. Now, if we look here, you see there are different angles between them. Now we want to find this angle theta. So the idea we are having here now, we want to find the angle between two planes. Okay, that's the second thing. But now it's not actually very hard, and that's quite surprising and interesting, because if we have two planes, suppose we have a plane here. Let's say this is a plane. I would color it with red. I have a red plane here. And suppose I have another plane, blue plane, like that. Maybe I shouldn't color them. Maybe it would just make things harder to see. And I have a blue plane that you would continue, right? I want to find this angle theta between these two planes. I want to find the angle between planes. Let's look at their normal vector. The normal vector to, let's call them A1 and A2. The normal vector to A1 is something like this. Let's show it with N1, right? This is normal. If I continue this plane to see it better, that would be something like that. The normal plane to A2 is something like this, N2. Right? Look at the angle between these two vectors. Actually, that's the same angle as the angle between the two planes. So angle between planes is equal to the angle between the normal vectors. Isn't it self-evident? I mean, isn't it kind of obvious when we are looking at the picture? So if you rotate one of them to get the other one, you can, in your mind, you can assume you can rotate A2 to get to A1. Yeah, that is completely correct. So if you rotate A2 to get to A1, suppose, for example, it's 30 degrees. So you rotate A2 by 30 degrees to get to A1. Now, if you have, well, I can explain better if I turn on my video. So if this is one of the planes and this is the other plane, right? I can think about rotating one plane to get to the other plane, right? So suppose I'm rotating it by, say, I don't know, 45 degrees to get to the other plane. Now, if this is a normal vector to one of them, if I rotate it to get to the other one, it would be the normal vector of the other one. But the amount I rotate my hand is the same amount as I rotate this normal vector. So that means the angle between two planes is equal to the angle between two normal vectors, N1 and N2. But we know how to compute the angle between two vectors. We should use the two different definitions we had for inner product. That's the way to compute the angle between two vectors. So if I want to answer this question, so suppose I have two different equations for two lines. Say the first plane, I'm sorry. Say I have a plane x minus 2y plus z equals 0. It's one plane. I have another plane, let's say 2x plus 3y minus 2z equals 0. Right, say I have two planes. This is one of them, this is the other one, A1, A2. I want to compute the angle between these two planes, theta, right? As I said, you should look at the normal vectors. What is the normal vector of A1? We should look at the coefficients. There is 1, minus 2, 1. Coefficient of x is 1. Coefficient of y is minus 2. Coefficient of z is 1. Let's look at A2. What are the coefficients of A2? Well, coefficient of x is 2. Coefficient of y is 3, coefficient of z is minus 2. So the angle between A1 and A2 is the same as the angle between N1 and N2. But what is that? Well, remember, we can use inner product to find that. What is the inner product of these two vectors? It's 1 times 2 plus minus 2 times 3 plus 1 times minus 2, which is equal to 2 minus 6 minus 2, which is minus 6. But there is another way of computing the inner product, and that's by multiplying the length of N1, the length of N2, and the cosine of the angle between them. Okay, what is the length of N1? So the length of N1 is the squared root of the sum of the square of its components. So it would be 1 squared plus minus 2 squared plus 1 squared, which is equal to square root of 6. What is the length of N2? It would be 2 squared plus 3 squared plus minus 2 squared, which is 4 plus 9 plus 4. It's square root of 17 cosine of theta. So square root of 6 times the square root of 17 times cosine of theta should be equal to the other way we computed cosine. Using this information, we see cosine of theta is minus 6 over square root of 6 square root of 17. We should use calculator to compute this number. This number is something around 0. Well, it's, first of all, it's negative, but it's minus 0.5, something like that. Okay, and what is the angle which gives us this thing? What is the arc cosine of minus 0.5? Well, it's almost, yeah, okay, you're correct, 126 degrees. It's minus 0.59. If you use calculator, you can see it's 126 degrees. So that's also the angle. Yeah, you're also right. If I keep it as, I mean, they're close to each other. So the angle is something around 126 degrees, and yeah. Okay. So that's the way you can compute another one. Let's give you one problem to solve. Okay, so find the angle. So if the angle between them is 0, it means they're parallel. Okay, if the angle between them, so this is one of them, this is the other one, it would be N1, this would be N2. The angle between N1 and N2 is 0, then it means they're parallel. Yep, thank you. Thank you for more accurate answers. So fine. So if the angle is 0, they're parallel. So it's kind of, we can use this method to completely understand if they're parallel or they will intersect. Find the angle between these two planes. Say 3x minus 4y plus z plus 2 equals 0, minus x plus 2y minus 3z plus 1 equals 0. Find the angle theta between these two planes. Okay, this is a question you might see in the exam. I want everyone to try to solve this. And then if you can't, ask me, and then I would explain.